All right, welcome, and as always, thanks for joining. So starting chapter 3.1. In chapter 3.1, we're going to be talking about functions that are really sort of new and different for a lot of you. So the one sort of piece of advice I want to give as we're going throughout this is now more than ever, it's going to be important that you jot down some note to the side of this. If there's something that you feel like you need clarification on or you just want discussed a little bit more, jot that down and we can talk about it in class the upcoming day. So 3.1. What we're going to be talking about in 3.1 and all throughout chapter 3 and sort of continuing into chapter 4 as well is the non-algebraic functions. So far, what we've looked at is algebraic functions, meaning that they were created by addition, multiplication, and roots, square roots, cubic roots. So now we're going to be looking at what are called transcendental functions, things that aren't functions based upon those operations. So the first one of those that we're going to discuss is the exponential function. An exponential function is a function in which the exponent is a variable or the exponent is a variable expression. So anytime I have something where x, for instance, is the exponent or in the exponent, that is an exponential function. An exponential function with base a is written as f of x equals a to the power of x, where a must be positive and a cannot be equal to 1, because if I had 1 to some power, I'm just going to keep getting 1. All right, we'll talk about some of these examples. So then to talk about the graph, I'm just going to draw us a little sketch real quick. When we're talking about the graph of any exponential function, or the basic exponential function, sorry, it's always going to pass through the point 0, comma. If I were to substitute 0 into this, I'd have a to the 0 power, and anything to the 0 power gives me 1. So 0, 1 is a point on this graph. Next, it passes through 1, comma. Whenever I put 1 into a basic exponential function, what I'm going to be left with is just a. And when we talk about a basic exponential function, we're talking about something that hasn't been shifted, reflected, stretched, anything like that. So here I have 1, comma, a, where a represents whatever the base is. This function also has a horizontal asymptote. And while it sometimes moves, the basic function has a horizontal asymptote of y equals 0. So that x-axis is our horizontal asymptote. And we've got this exponential function. And I will move that point so that it's actually on the exponential function. There we go. So we get this graph. An exponential function continues on in both directions, left and right. It's always going to be increasing or decreasing throughout. And it always has that horizontal asymptote. All right, moving along to transformations. Reflections. If we're talking about reflections, we have reflections over the x-axis and over the y-axis. A reflection over the x-axis means I'm changing the y value. And when I'm changing the y value, what I'm doing is making the entire function also known as your output, opposite. If I'm reflecting over the y-axis, I'm changing my x values, which is just going to be making the input opposite. Shifting. And when we talk about shifting, there's two types again, vertical and horizontal. A vertical shift is any time that we add or subtract outside the exponent. Horizontal, this is subtract. Horizontal is anytime that we add or subtract inside the exponent. Back in chapter 1.4, we talked about horizontal shifting, and one of the sort of things you could recognize is that anything that was horizontal was happening inside parentheses. Exponents sort of have their own unwritten or implied parentheses, so they are still sort of there. Stretching and shrinking is managed by the a value. So for right now, we won't worry about too much of the stretching and shrinking. All right, we'll skip a couple or one slide. So then we're going to talk about the natural base, e. E is an irrational number that is used in many natural exponential growth and decay situations. So it's just a naturally occurring number, and it's used a lot in growth and decay. And we'll talk about other places where it's used as well. E is a constant. You sort of think of E as like pi is 3.14. What E is approximately 2.71828. It can be approximated by the equation 1 plus 1 over x to the power of x when x approaches infinity. And this is not particularly important for you, but just sort of in the back of your mind, you could be thinking, there is something that gives us e. It's 1 plus 1 over x to the power of x as x goes on to infinity. E can be found in two places on your calculator. Make sure that you remind us so that we can point out where those two places are. One of them a little bit more helpful than the other. Since E is a constant, all graphs of f of x equals e to the power of x will behave in the same way as f of x equals a to the power of x. So e, not a variable. It's just a number. It's an irrational number, which is fine. So it has all those same properties of a graph as a to the power of x. All right, and then the last thing I want to talk about is the compound interest formula. So compound interest formula, after t years, the balance, which we call a, in an account with principal P and annual interest rate R is given by the following formulas. So for n compoundings per year, if I'm telling you how often I'm going to essentially compound that interest, that formula is given by A equals P times 1 plus R over N raised to the power of NT, where T is time in years. And it's important that it's in years. Continuous compounding is a different formula, so that's going to be A equals P, then E, that natural irrational number, that natural base E, to the RT. We'll use those two formulas a little bit in the examples video, and you'll see some applications of that then. All right, that's all we're covering for section 3.1 notes. Especially go back, watch a couple of those important slides just with that exponential function, how that's supposed to look. Otherwise, make sure you write down any questions that you have and bring them, be willing to ask them.